Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss Carnot's heat engine. Let's begin. In the previous video lecture, we discussed about heat engine. In heat engine, the efficiency of heat engine we have calculated, but here we see the efficiency of any heat engine will not be 100% efficient. So, to avoid this type of theoretical understanding, the scientist CARNOT'S proposed a theoretical view regarding Carnot's heat engine, that it indicates how a heat engine is created to produce 100% efficiency. So, this is about a theoretical proposal that proposed by scientist Carnot, and it has no such practical way to design that one. So, the Carnot's heat engine consists of 5 parts. The parts are like cylinder, source, sink, insulating stand, fifth, working substance. These 3 parts like source, sink and working substance are same as that of heat engine, but new thing, that is cylinder and insulating stands, are added to that of Carnot's heat engine. What is cylinder? It is a cylinder with perfectly insulated walls and perfectly conducting bottom, and it is fitted with a perfectly insulated, frictionless and weightless piston. So, I draw that a figure. How to draw that cylinder here? These are insulated walls and the bottom is conducting one. This is also the piston is insulated piston, which is perfectly elastic, frictionless and weightlessness. Inside that of piston, we use the working substance. Working substance, in that of case, 1 mole of an ideal gas is taken at the working substance enclosing in that of cylinder. Here we take 1 mole of ideal gas. That is, this one is the cylinder. Next part, source. What is source? Source, it is a hot body. As we studied in that of heat engine, it is a hot body, or we can say as a reservoir that maintained at a constant high temperature, let T1 degree Kelvin. It has very large thermal capacity such that if certain amount of heat is taken out from that of source, its temperature should remains constant or remains unchanged. That is why it is a large thermal capacity. So, let I draw the source. This is the source at T1 degree Kelvin. That is a hot body. Next, sink as same in that of heat engine. It is a cold body, or we can say as a reservoir to maintain a constant lower temperature at T2 degree Kelvin, and similarly it has very large thermal capacity such that if certain amount of heat is given to that of sink, its temperature should remain unchanged. So, we draw here the sink. That is sink at T2 degree Kelvin temperatures. Next, insulating stand. Insulating stand, it is a perfectly insulated stand, or we can say that is the pad. Here is the insulated stand. This one is the insulated stand. Insulated stand. This is the insulated stand. These are the parts of Carnot's theoretical heat engine, that is cylinder, source, insulated stand and sink. Now, Carnot's cycle. In Carnot's reversible cycle, the working substance is taken over 4 different steps. Here the steps are 2 isothermal and 2 adiabatic changes. How these processes are carried out, let take a look here. First, Carnot's cycle, first step, isothermal expansion. How isothermal expansion is taken into consideration. So, isothermal expansion in Carnot cycle, first of all, place that cylinder containing 1 mole of ideal gas on the source. That cylinder place on that of source. What happened? So that the gas acquires a temperature of T1 degree Kelvin of that of source. When that gas is placed on that of source, that gas acquires a temperature of T1 degree Celsius as that of source. And let pressure and volume of that of gas at initial state be P1 and P2. Sorry, P1 and V1. P1 with the initial pressure and V1 the initial volume of that of gas at initial state. This initial state we can represent as a point. Let we represent the PV diagram here. We represent the PV diagram here. Here the volume and here let the pressure. At initial point, let the point be A here. Here let the point be A. At initial point A, the gas acquires the pressure as P1 and volume as V1, that denoted by that point. Okay. Now we just cylinder put on that of source. Now gas is allowed to expand quasi-statically. Quasi-statically process in thermodynamics is that process, that thermodynamic process proceeds very slowly in the sense at each step that process is seen to be thermal equilibrium. This type of thermodynamic process is said to be quasi-static, means it proceeds very slowly. So when that ideal gas or that cylinder placed on that of source, and that ideal gas acquires a temperature of T1 degree Kelvin, so the gas is allowed to expand quasi-statically, and the piston, that piston moves slowly and slowly upward till the gas reaches at the point, at let that point B, reaches that point B, acquiring the pressure as P2 and volume as V2, where P2 and V2 are the pressure and volume of that of gas. As the gas expands, its temperature falls and heat is absorbed from the source, and temperature of that of gas again becomes T1 degree Kelvin. During this process of expansion, temperature remains constant, that is T1 degree Kelvin during that expansion. Hence it is a process of isothermal expansion. So that process is termed as isothermal expansion. Throughout that of total expansion, the temperature remains constant. Now that process, here is the process, step 1, that is the isothermal expansion. Here is the isothermal expansion. We have to calculate what should be the work done during that of isothermal expansion. In this process of isothermal expansion, the gas moves from that of state A at P1 V1 to that of state B at P2 V2, and it is represented by that of curve AB on that of PV diagram, which is known as the indicator diagram. Let me write, let the amount of heat absorbed, here I write, let the amount of heat absorbed, the amount of heat absorbed by the gas from source is equal to, let Q1 amount of heat is absorbed by the gas from the source. Now we know the work done during isothermal expansion from the state from the state A to B. What should be the work done? So we know that work done during isothermal expansion from state P1 V1 to state point B at P2 V2 is given by that means work done, let I say, that is W1. According to the work done expression for isothermal process, we say it as from V1 to V2 PdV will be how much? The expression, according to the expression, it will be W1 is equal to R T1 log V2 by V1 of base E, that is the work done. So that amount of work done can be easily understood with the help of that PV diagram. So here in that of diagram, the work done will be the area under that of curve AB. So the area under that of curve AB, let I draw the strip here, draw the strip. The points are, let A dash, here is the point as B dash, that means the area under the curve A dash, B dash, BA. So that work done is the area A, B, B dash, A dash, A, that is the area under that of particular curve AB, which is isothermal expansion. Now in this process, the whole of the heat absorbed by the gas is converted into work. So Q1 is same as W1. Here I write, in this process what happened, in this process whole of heat, the total heat, the whole of heat absorbed by the gas, absorbed by the gas is converted into work, is converted into work. So Q1 is same as W1, and therefore Q1 is equal to W1 is equal to R T1 log base E V2 by V1, that is area under, that is area of A, B, B dash, A dash, A. Just box it. In first step of Carnot cycle, we have that amount of work done during the expansion AB. Now means first we just place that cylinder on that of source. Again what happened to that of step 2? Step 2, which is known as adiabatic expansion. How adiabatic expansion takes place? Look here, what we take, that cylinder. Now remove the cylinder from the source and place it on that of insulating stand. Just replace on source and place it on insulating stand. Now the gas is completely thermally isolated from the surroundings. Since it is insulated wall, now that gas, means inside that of cylinder we consider 1 mole of gas, that gas is completely thermally isolated from the surroundings. Now allow the gas to expand till it reaches the point, let we take that of point at C. We allowed that gas to reach the point, let here is the point C having coordinates P3 V3. Allow the gas to expand till it reaches the point C at P3 V3, and its temperature gradually decreases and becomes T2 degree Kelvin. This process is an adiabatic expansion. This process, that process from B to C, from B to C, the process, that process is an adiabatic expansion. Throughout the expansion heat is constant, that is the adiabatic expansion. And in this adiabatic expansion, in that of adiabatic expansion process, the gas moves from state B, that coordinate P2 V2, to that of state C, that coordinate P3 V3. These are the pressure and volume respectively, and it is represented by that of curve BC in that of PV diagram. No heat is absorbed by the gas during this process. No heat is absorbed by that of gas during this process. In that of process, heat is constant, and the work is done by the gas at the cost of internal energy. Since there will be no heat absorption takes place, so the work is done on that of gas, the work is done by the gas due to the internal energy. So we can say what happened in that of adiabatic expansion here, how work done is proceeds. So in step 2, that is adiabatic expansion, what happened? No heat is absorbed. So I write here, no heat is absorbed by the gas during this process, and work is done by the gas, due to its internal energy, So what should be the work done during that of adiabatic expansion? So the work done, therefore we write work done during adiabatic expansion, from state B, having coordinate P2 V2 to state C having coordinate P3 V3 is given by let work done be W2 is equal to integration from V1 to V2 PdV, and that is R divided by gamma minus 1 T1 minus T2, that is W2. As we know, the expression for the adiabatic case, the work done will be that much. And what is the work done? We have to calculate from that of PV diagram, that the area under that of curve BC. So the strip will be here, the point B C dash, that is the area under B dash C dash C B. So right here, that is the area B C dash B dash B, that is the expression for work done during that of adiabatic expansion, case number 2. Next, step 3, isothermal compression. Here is the compression. How? Let we see that of figure. First of all, we take that cylinder on source, then insulating stand, then now remove that cylinder from insulating stand and place it on that of sink, which is a temperature of T2 degree Kelvin. Now slowly push the piston downward, piston of that of cylinder. The gas is compressed and its temperature rises. The heat will flow from gas to the sink and its temperature becomes T2 degree Kelvin. Hence temperature remains constant during the process. and this process is isothermal compression. That compression proceeds in that of isothermal process. Throughout that of process, temperature remains constant. Continue to move the piston downward till the gas reaches the state at D. We just continue that process. When that state reaches to that of point D, and its coordinates P4, V4, pressure and volume at constant temperature T2 degree Kelvin, since it is isothermal compression. So, in that of process of isothermal compression, gas moves from that state C having coordinate P3 V3 to the state D having coordinate P4 V4, and it is represented by that of curve CD under that of PV diagram. Let here Q2 amount of heat is rejected by that of gas to the sink, and this amount of heat is used in which purpose? So, let Q2 amount of heat, let in that of isothermal compression, let Q2 amount of heat is rejected by the gas to sink, and which is equal to the work done on the gas, that is the work done on the gas, in previous one that is by the gas, but here this is the work done on the gas, that is Q2 is same as W3 with the work done on the gas. Let work done during that of isothermal compression. So, work done during isothermal compression, from state C having coordinate P3 V3 to D having coordinate P4 V4 is given by that is W3 is equal to integration from V3 to V4 P minus dV, that will be negative integration from V3 to V4 P dV. Since it is isothermal process, the work done is same as, that is R T2 log V3 V4, just overcome that of negative sign, it will be V3 by V4, that is the area under that of curve. Look here that figure, just I draw that of strip here, that the area under that of curve D dash C dash C D. So, that is the area under C D dash C dash C. So, that W3 is same as Q2. So, Q2 is equal to W3 is equal to what? R T2 log V3 by V4 having base E is equal to area under that of curve C D dash C dash C. That is the work done during that isothermal compression. Now here we stay the cylinder in that of sink. Now remove the cylinder from the sink and place it on that of insulating stand. Again the gas is completely thermally isolated from that of surroundings. Now compress that gas adiabatically till it reaches to that of initial state P1 V1. Look that of figure, we compress it till that achieves the initial state P1 V1. And the temperature becomes T1 degree Kelvin here. In this case no heat is absorbed by the gas, and in this process of adiabatic compression gas moves from the state D having coordinate P4 V4 to that of state A having coordinate P1 V1, and it is represented by the curve dA on that of PV diagram. So what should be the work done here? Here I write, in that of adiabatic compression throughout that of process heat is constant and it is compression. So the work done during this adiabatic compression, work done during this adiabatic compression is given by, that is W4, which is equal to integration from V4 to V1 P minus dV, that is the compression case. So it will be positive when we change its limit, means it will be positive when we change the limit from V1 to V4, that is P dV. So in case of adiabatic process the work done is given as R T1 minus T2 divided by gamma minus 1. From the PV diagram it will be the area under that of curve A dash D dash D, that is area under the curve, area D A dash D dash D, or we can write here W4 is equal to R T1 minus T2 by gamma minus 1 is equal to area under D A dash D dash D. Not the work done in that case, in that of adiabatic compression. Look here, these 4 cases, that is isothermal expansion, this is adiabatic expansion, then isothermal compression, and here adiabatic compression. 2 compression, 2 expansion, 2 isothermal case, 2 adiabatic case. So what should be the total work done? Let me calculate the total work done. First of all we see, since work done by the working substance is positive and work done on the working substance is negative, this is the sign convention. Work done by the working substance is positive and work done on the working substance is negative. Hence W1 and W2 is step 1 and step 2 are positive. W1 and W2 are positive. Let I write here according to the sign convention. W1 and W2 are positive, W3 and W4 are negative. And also again another sign convention, heat gained by the working substance is positive and heat lost by the working substance is negative. Heat gained by that working substance is positive and heat lost by the working substance is negative. Hence Q1 is positive and Q2 is negative, since Q1 is the heat gained and Q2 is the heat loss. So overally, using this sign convention for work done and heat, we write hence the total work done, net work done by working substance during complete cycle, that is W total work done, that is W1 plus W2 minus W3 minus W4 according to the sign convention. So here W1, that is area under the curve AB, B dash A dash A plus W2, that is area under the curve BC, C dash B dash B minus W3, that is the area under the curve CD, D dash C dash C minus for W4, that is area under the curve D A dash D dash D, and here W2 is same as W4. Here W2 is same as W4. So these two terms are cancelled. W2 and W4 are cancelled with each other. So we have, or W is equal to, that is W1 minus W3, which is the area of A, B, C, D, A. Look at the figure, W1 minus W3, that is the area A, B, C, D, under that area A, B, C, D, here that area. So that is W1 minus W3 can be written as that is Q1 minus Q2, which is the area A, B, C, D, A, and that overall thing is nothing, that is the area of Carnot's cycle, and that cycle from A, B, C, D, A. So that is the total work done during in an Carnot's cycle. Now we have to calculate what should be the efficiency of that Carnot's heat engine. So efficiency of Carnot's heat engine, right here, efficiency of Carnot's heat engine is given by, that is eta will be 1 minus Q2 by Q1. So eta is equal to 1 minus, in place of Q2, that is R T2 log V3 by V4 base E divided by R T1 log V2 by V1 base E. R cancel out. So eta is equal to 1 minus T2 log V3 by V4 base E divided by T1 log V2 by V1 of base E. See here, from that of figure, look here from that of figure, the point B, C lie on the same adiabatic process BC, and the point A and D again lie in that of same adiabatic dA. So, according to the adiabatic equation, we can write here, since point B and C lies on the same adiabatic BC, therefore what we have, T1 V2 to the power gamma minus 1 is same as T2 V3 to the power gamma minus 1. Again since point A and D lies on the same adiabatic dA, therefore T1 V1 to the power gamma minus 1 is same as T2 V4 gamma minus 1. Let that is equation number 1, that is equation number 2. Now dividing this, we have dividing equation equation 1 and 2 means 1 by 2, we get T1 V2 to the power gamma minus 1 divided by T1 V1 to the power gamma minus 1 is equal to T2 V3 to the power gamma minus 1 divided by T2 V4 to the power gamma minus 1, or that is V2 by V1 to the power gamma minus 1 is same as V3 by V4 to the power gamma minus 1. Let that can be changed to V2 by V1 same as V3 by V4. Again taking the logarithm on both sides, that is log of base e of V2 by V1 same as log of base e V3 V4. That means V2 by V1 of log e is same as V3 by V4 of log e. So these two quantities are same. Now these two are cancelled with each other. So let we take putting these values in eta. Therefore the efficiency eta will be how much? 1 minus T2 by T1. The efficiency will be 1 minus T2 divided by T1. This is the expression, that is the expression for efficiency of Carnot's cycle, of Carnot's heat engine, and the efficiency of Carnot's heat engine. Now what indicates that particular expression? From this expression you see here that depends upon the temperature of the source and sink. The efficiency depends upon that depends upon temperature of source and sink only, and again it is independent of the nature of working substance. It is independent of the nature of working substance, and finally more is the temperature difference between the source and sink, this is the source, that is the sink. More is the temperature difference between source and sink, more is the efficiency. So, more is the temperature difference between the source and sink, more is the efficiency, eta. Okay. Now, look that of particular expression, eta that is 1 minus T2 by T1, that is same as 1 minus Q2 by Q1, since T2 as Q2, T1 as Q1. Therefore, Q2 by Q1 is same as T2 by T1, that expression. In that of case, if T2 as 0 degree Kelvin, if T2 is 0 degree Kelvin, then T1, then Q2 also 0, then Q2 also 0, and putting that value here, therefore eta is equal to 1. That means we get 100% efficiency, but actually, T2 is equal to 0 degree Kelvin is impossible, and also Q2 is equal to 0 degree Kelvin is again impossible. In other words, it is not possible to convert whole of the heat absorbed from that of source into mechanical energy without rejecting a part of to the sink. That means it is not possible to create a heat engine having 100% efficiency. That can be understood from that of particular expression. So, this all about regarding the theoretical construction of heat engine by Carnot's, which is known as Carnot's heat engine. So, with the help of this video lecture, we understand what is Carnot's heat engine, its different parts and its functional analysis, as Carnot cycle, isothermal expansion and work done during that isothermal expansion. Then step 2, adiabatic expansion and work done during that of adiabatic expansion, isothermal compression, work done during that of isothermal compression, adiabatic compression and work done during that of adiabatic compressions. These are the 4 steps or 4 cycles of that of Carnot's heat engine, and finally the total work done during that of particular Carnot cycle, and finally the efficiency of that of Carnot's heat engine. This is the expression for that of efficiency of Carnot's heat engine. From that of expression, what are the outcomes, and finally how we can construct a heat engine having 100% efficiency. This is the cause why it is not possible. So, with this useful and informative notes, let me wind up this session. Thank you.